Now let's take this concept of electric field one step further. And I suspect some of you guys might even have an idea where we're going here. Let's look at that gravitational equation again. We looked at gravity. If we were on some planet X, and you were a person standing on that planet, right, you would have a certain weight associated at that planet, right, due to your mass. And we could figure out exactly how you would accelerate at the surface of that planet, right? And so, we learned initially how to calculate the acceleration due to gravity on any planet, and that would be big G times the mass of the object, in this case it would be planet X, over the distance to the center of that object squared, which would be its radius. And that's how we found the acceleration due to gravity in newtons per kilogram or meters per second squared. Well, that applied to any object on that surface, but if I wanted to know exactly what force they would feel, or in this case, their weight, right, we know that weight is really the same as the force of gravity. And the way we found weight was we always took the mass of the object times the acceleration due to gravity, or the mass of the object times its field strength. Right? So that would be the same as saying mass times big G, mass of the planet over the distance to the center squared. And this allowed us to derive an equation for the force of gravity between any two objects. Big G, the mass of one object, which is usually the planet, the mass of the second object, the person standing on that planet or some distance away, over that distance squared. And if you recall, this is what we call Newton's law of universal gravitation. And the way I taught it as field strength first, and then brought a mass into the field to get our new equation. And I think you guys can see what we might be doing with our electric field. Well, we've only done field strength thus far, but we've seen that gravity and field and electric fields are analogous. The field strength of gravity is similar to the field strength of an electric field. The mass in a gravitational field is similar to a charge in an electric field. Well, if that's the case, then the weight or the force of gravity in a gravitational field, which is just mass times the field strength of gravity, Ag, well, you could probably extrapolate that the force of an electric field would just be the charge times the strength of the electric field. And in fact, that is our equation for the force on an object in an electric field. Right? This is the charge of the object in the field and this is the field strength. And if you look at the units, well, charge would be coulombs, and field strength is in newtons per coulomb. Coulombs cancel, and so I'm sure some of you guys figured out, hey, I could probably find the forces on these objects. Right? And if you take it one step further, we see another form of this same equation. Just like we did with our gravitational force equation, you could plug in what we know for field strength E to get another equation for the electrostatic force. The force of an electric field is equal to K, or rather Q times KQ over D squared, and that's the source, which gives you, if I simplify it, sometimes it's written this way. K, Coulomb's constant, the charge of one object, the charge of the other object over the distance squared. And with the gravitational one, it was Newton's law of universal gravitation. And hopefully you can guess what this one is. Well, this is Coulomb's law. A lot of textbooks start here and then work backwards to electric field, but I've kind of taught it in reverse, and I think it makes a little bit more sense this way. But now all we got to do, if I know the field strength E, and I actually have a charge, not a test charge anymore, but an actual electron or some amount of charge brought into the field, I can figure out the forces. And in fact, if I have two sources, let's say we have the two balloons we were looking at before. Well, what force do they pull on each other? Right? So let's look at a quick example. All right, before, if you look up, we had two balloons. One was 20 microcoulombs, one was 60 microcoulombs. All right, two balloons. Are 50 centimeters apart. And I want to know, well, what is the force of the first balloon, balloon A, on balloon B? Balloon A was, I believe, negative 20 microcoulombs. And I want to know, what is it doing to balloon B, which was negative 60 microcoulombs. And just like before, we can draw a quick picture. You have balloon A and balloon B. Now I don't care about the point in the middle anymore. What I do know is this is negative 60 microcoulombs and this is negative 20 microcoulombs. We know the total distance is a half a meter apart, right? 50 centimeters. And A is going to do what to B? Well, they are the same charge, so there should be a force to the right on B, right? A should repel B. And so I'm going to draw an arrow to the right. This is the force of A on B. And so a couple ways to do this. We can find the field of A and multiply it by B, or we can plug it right in to Coulomb's law. So option one would be to find the field of A at B's location, right? In which case the field of A would be K, the charge of A, over the distance to A squared, 9 times 10 to the 9. The charge of A is 20 times 10 to the negative 6, and the distance is a half a meter. And we square that. And if I pull out my calculator, alpha K times 20 second E to the negative 6 and divided by 0.5 squared. Again, it's the full distance now. And I get 720,000 newtons per coulomb. Well, then the force is just going to be the charge of B times the field that it's in. It's in A's field, which would just be 60, so I'll keep the colors consistent, times 10 to the negative 6, times that field strength, 720,000. So if I take that value and multiply it by 60, second E to the negative 6, I get a value of 43.2 newtons. The force is equal to 43.2 newtons. All right, so probably a little stronger than what an actual balloon would be, so these charges aren't probably super accurate, but nonetheless, you get a value that seems relatively reasonable. That's option one, find the field and then bring B into it, or we could jump right to option two and use Coulomb's law, which is really, again, the same thing. The electrostatic force is equal to K. In this case, it's the charge of A, the source. The charge of B, the charge brought into the field, this is A's field, over the distance between them squared. And when you plug in, you got 9 times 10 to the 9. You have the charge of A, which is 20 times 10 to the negative 6. The charge of B, which is 60 times 10 to the negative 6, all over 0.5 squared. And when you plug that in, you should get the exact same value for that force of 43.2 newtons. Now notice something I did here. What happened with those signs? Right? I had negative signs in here in my original numbers, but I didn't put my negatives anywhere in this problem. Right? And the way it ends up working out is if I get an answer that is positive, then it's repelling. If it's negative, it's attracting. Right? So technically, I can put the signs in there, and I would get a force that's positive. All that just means is that it is going to repel. All right? So I'm just going to say it's repulsion. In this unit, my advice to you is don't worry about putting any negatives in your calculations. Right? Draw a picture. Use the picture to determine that B should be repelled by A based on the fact that they're opposite signs. Right? So ignore the signs in your problems. We'll see more like this, and we'll see where the signs come into play even more. But again, that would be my advice to you. Draw a picture to determine what direction.